This is part 2 of Euclid Book 2, proposition number 11. And what we're going to do is we're going to start with this right angle triangle right here that starts at E, goes to B, and goes over here to A. And as we already know, angle EAB is a right angle. Okay, we know that. Now, the square on BA, well, here's BA right here, and the square on AE, which is right here, is equal. If you added the area of both of those squares, it would be equal to the area of EB, which is right here. Okay? Now we're going to have a square on EB. And I already told you about this in the last video. Okay? So you have a square here, and a square here, and if you were to add the two squares here, you'd have the square here. Okay? And that's because EAB is a right angled triangle. Okay? And all this can be proved by Euclid Book 1, propositions number 46 and 47. 46 is needed to draw the three physical squares you're going to need to prove all this. And number 47 is needed to actually prove the proof. It is the Pythagorean theorem. Okay. Now, excuse me. We have a rectangle, CFFA. Now, first of all, that triangle, rectangle we're talking about is actually CFFG. But as I told you in the previous video, this G here could be replaced with the letter A because FA equals the length of FG. So this entire area here is what we're going to talk about now. Alright, so we got rectangle CFFA, and then we're going to add the area of square AE. Okay, where is the square of AE? Well, here's letter A, here's letter E, and we got a square right across in here. Okay, so the area inside of square AE added together with the area inside this rectangle, which is CFGK, or otherwise known as CFAK, okay? If you were to add those two areas together, then you would have the same amount of area as though you were going to add BA, okay? So we have a square on BA. Remember, as I was telling you in Euclid Book 1, proposition 47, we're going to use it here. We're going to have a square on BA. So the area of BA plus AE. Okay? So this rectangle plus AE equals the square of BA plus AE. Okay? Now, we're going to subtract the area of AE from this rectangle, and we're also going to subtract the area of AE from the total of the area of AE and BA. Okay? And when we do this, then we can say that the area inside of CFFA, this rectangle right here, is equal in size to the square of BA. So if we drew a square around BA, this area inside of that square would be equal in size to the area of CFAK. Alright. Now, we've now said that the rectangle CFFA is actually CFGK. Okay, that's because this line here is equal in size to this line here. So we can say that this rectangle was CFAK, or we could actually say it's CFGK as it's actually marked. Alright. Now, the square of AB. Where is the square of AB? Well, AB is right here. We'd have a physical square right across here. And it is actually equal in size to ACDB. ACDB. Why is this? Because whether the square is drawn up here or drawn down here, it's going to be the same size. Alright? Because this line is equal to this line, is equal to this line, is equal to this line. And we're going to put two lines right here Okay, so this side, and this side, and this side are all equal. And if we were to draw the square of AB up in here, we'd have the same three more other sides equal to these three sides here. Alright? So, the square AB is actually ACDB in this case. So we can say that rectangle CFGK is equal in size, equal in area, the area inside this rectangle is equal in area to ACDB. ACDB. Okay? The area inside of here, this whole square here, is going to be the same amount of area as what's in this rectangle right here. Alright. And that's where I'm going to stop this video here. And I will tell you the rest of it in the next video, so stay tuned.